Prime numbers. In this video, we are going to see about prime numbers. Prime numbers play a critical role in number theory and cryptography. Any integer p greater than 1 is a prime number if and only if its only divisors are plus or minus 1 and plus or minus p. To get number of prime numbers in a certain range, alpha is equal to product over p belongs to p power ap, where ap is greater than or equal to 0. P, set of all prime numbers. P, possible prime number for particular values a. A, integer. Multiplication of two numbers is equivalent to adding corresponding exponents, that is powers. A is equal to product of p belongs to p power ap. B is equal to product of p belongs to p power bp. So, k is equal to a into b. The integer k can be expressed as a product of powers of prime as k is equal to product of p belongs to p power kp. That is, kp is equal to ap plus bp for all p belongs to p. K is equal to 12 into 18 is equal to 2 square into 3 into 2 into 3 square is equal to 216. K2 is equal to 2 plus 1 is equal to 3. K3 is equal to 1 plus 2 is equal to 3. 216 is equal to 2 cube into 3 cube is equal to 8 into 27. In terms of prime factors of a and b, to say that a divides b. Any integer of the form p power n can be divided only by an integer that is lesser or equal power of the same prime number p power j with j less than or equal to n. A is equal to product over p belongs to p power ap. B is equal to product over p belongs to p power bp. If a is divided by b, then ap is lesser than or equal to bp for all p. A is equal to 12, b is equal to 36. 12 divided by 36. 12 is equal to 2 square into 3. 36 is equal to 2 square into 3 square. A2 is equal to 2 equal to b2. A3 is equal to 1 lesser than or equal to 2 is equal to b3. Thus, the inequality AP is lesser than or equal to BP is satisfied for all prime numbers. It is easy to determine the greatest common divisor of two positive integers if user expresses each integer as a product of primes. 300 is equal to 2 square into 3 power 1 into 5 square. 18 is equal to 2 power 1 into 3 square. GCD of 18, 300 is equal to 2 power 1 into 3 power 1 into 5 power 0 equal to 6. The following relation always holds. If k is equal to GCD of a, b, then kp is equal to minimum of ap, bp for all p. Formulating the prime factors of a large number is not an easy task, so the preceding relationship does not directly lead to a practical method of calculating the greatest common divisor. Primality testing. In this video, we are going to see about primality testing. A primality test is an algorithm for determining whether an input number is prime or not. In cryptography, the prime number has its own importance. There is no simple yet efficient means of accomplishing the task of finding prime numbers. It is important to note the difference between primality testing and integer factorization. Since 2006, factorization is a computationally hard problem, whereas primality testing is comparatively easy. Suppose the user has an integer of 200 digits and they have to find out the prime numbers. There are around 4 into 109 primes less than 10,100. If the computer can handle 109 primes per second, the calculations would take around 1081 years. Naive method. The simplest primality test is as follows. Given an input number n, if any integer m from 2 to n-1 divides n. If n is divisible by any m, then n is composite, otherwise it is prime. Rather than testing all m up to n-1, user need to test m up to j. If n is composite, then it can be factored into two values, at least one of which is less than or equal to root n. User can also improve the efficiency by skipping all, even m expect 2, since if any even number divides and then 2 does. User can further improve by observing that all primes are of the form 6k plus or minus 1, with the only exceptions of 2 and 3. This is because all integers can be expressed as 6k plus I for some k and for I is equal to 1, 0, 1, 2, 3 or 4. 2 divides 6k plus 0, 6k plus 2, 6k plus 4 and 3 divides 6k plus 3. User needs to test if n is divisible by 2 or 3, then run through all the numbers of form 6k plus or minus 1 less than or equal to square root of n. This is 3 times as fast as the previous method. In fact, all primes are of the form c hash k plus I for I is less than c hash, where I represent the numbers that are co-prime to c hash. In fact, as c tends to infinity, the number of values that c hash k plus I can take over a certain range decreases, and so the time to test n decreases. For this method, divide all primes that are less than c. Observations analogous to the preceding can be applied recursively, giving the sieve of Eratosthenes' method. A good way to speed up these methods is to pre-compute and store a list of all primes to a certain bound, say all primes up to 200. Then, before testing n for primality with a series method, one first checks whether n is divisible by any prime from the list. Probability test. Most popular primality tests are probabilistic tests. These tests use, apart from the tested number n, some other numbers a, which are chosen at random from some sample space. The usual randomized primality tests never report a prime number as composite, but it is possible for a composite number to be reported as a prime. The probability of error can be reduced by repeating the test with several independently chosen as for two commonly used tests. For any composite n, at least half as detect n's compositeness, so k repetitions reduce the error probability to at most 2-k, which can be made arbitrarily small by increasing k. The basic structure of randomized primality tests is as follows. Pick a random number a. Check some equality involving a and the given number n. If equality fails to hold true, then n is a composite number. A is known as a witness for the compositeness, and the test stops. Repeat the first step until the required is achieved. After several iterations, if n is not found to be a composite number, then it can be declared probably prime. Fermat primality test. Fermat primality test is the simplest probabilistic primality test. It is only a heuristic test. some composite numbers will be declared probably prime no matter what witness is chosen. Nevertheless, it is sometimes used if a rapid screening of number is needed, for instance in the key generation phase of the RSA key cryptographical algorithm. Let n is greater than 1 be an integer. Choose a random integer a with 1 less than a less than n minus 1. If a power n minus 1 is not equal to 1 mod n, then n is composite. If a power n minus 1 is equal to 1 mod n, then n is probably prime. Miller-Rabin primality test. The Miller-Rabin primality test and the Solovay-Strassen primality test is more sophisticated variants which detect all composites. They are often the methods of choice as they are much faster than other general primality tests. Let n greater than 1 be an odd integer and n minus 1 is equal to 2 power k m with m odd. A is random integer such that 1 is less than a less than n minus 1. Calculate b0 is equal to a power m mod n. If b0 is equal to l minus 1 mod n, then stop and n is probably prime. Otherwise, b1 is equal to b0 power 2 mod n. If b1 is equal to 1 mod n, then n is composite. If b1 is equal to minus 1 mod n, then declare n as a probably prime. Otherwise, b2 is equal to b2 power 2 mod n. Otherwise, b2 is equal to 1 mod n, then n is composite. If b2 is equal to minus 1 mod n, then stop and declare n as a probably prime. Continue the process until bk minus 1. Factorization. In this video, we are going to see about factorization. Factorization plays a very important role in the security of several public key crypto systems. Fundamental theorem of arithmetic. According to the fundamental theorem of arithmetic, any positive integer greater than 1 can be written uniquely in the following prime factorization form. N is equal to p1 to the power e1 into p2 to the power e2 into and so on up to pk to the power ek, where p1, p2 and so on up to pk are primes and e1, e2 and so on up to ek are positive integers. There are immediate applications of factorization such as the calculation of greatest common divisor, the least common multiplier, greatest common divisor. A is equal to p1 to the power a1 into p2 to the power a2 into and so on up to pk to the power ak. B is equal to p1 to the power b1 into p2 to the power b2 and so on up to pk to the power bk. GCD of a comma b is equal to p1 to the power of minimum of a1 comma b1 into p2 to the power of minimum of a2 comma b2 and so on up to pk to the power of minimum of ak comma bk. Least common multiplier. A is equal to p1 to the power a1 into p2 to the power a2 into and so on up to pk to the power ak. B is equal to p1 to the power b1 into p2 to the power b2 and so on up to pk to the power bk. LCM of a comma b is equal to p1 to the power minimum of a1 comma b1 into p2 to the power minimum of a2 comma b2 and so on up to pk to the power maximum of ak comma bk. It can be proved that GCD of a comma b and LCM of a comma b are related to each other as shown below. LCM of a comma b into GCD of a comma b is equal to a into b. Factorization method. There has been a long search for efficient algorithms to factor large composite numbers. Unfortunately, there is no perfect algorithm has been found. Although there are several algorithms that can factor a number, none is capable of factoring a very large number in a reasonable amount of time. The process of factorization is time-consuming. Trial division method. The simplest and least efficient algorithm is the trial division factorization method. Forum discussion on the sieve of Eratosthenes. If n is composite, then it will have a prime. P is less than or equal to square root of n. The following algorithm shows the pseudocode for this method. The algorithm has two loops, one outer and one inner. The outer loop finds a unique factor. The inner loop finds duplicates of a factor. For example, 24 is equal to 2 cube into 3. The outer loop finds the factor 2 and 3. The inner loop finds that 2 is a multiple factor. Complexity. The trial division method is normally good if n is less than 2 power 10, but it is very inefficient and infeasible for factoring large integers. The complexity of the algorithm is exponential. Fermat method. The Fermat factorization method's algorithm divides a number n into two positive integers a and b, not necessarily a prime, so that n is equal to a into b. The Fermat method is based on the fact that if user can find x and y such that n is equal to x square minus y square, then n is equal to x square minus y square is equal to a into b, with a is equal to x plus y and b is equal to x minus y. This method tries to find two integers a and b close to each other. A is approximately equal to b. It starts from the smallest integer greater than x is equal to square root of n and tries to find another integer y such that the relation y square is equal to x square minus n holds. The whole point is that in each iteration the user needs to see if the result of x square minus n is a perfect square. If user finds such a value for y, they calculate a and b and break from the loop. If user does not, they can do another iteration. Complexity. The complexity of the Fermat method is close to sub-exponential. Pollard P-1 method. In 1974, John M. Pollard developed a method that finds a prime factor p of a number based on the condition that p-1 has no factor larger than a predefined value b, called the bound. Pollard showed that in this case, p is equal to GCD of 2 power b factorial minus 1, n. The following algorithm shows the pseudocode for Pollard P-1 factorization method. Complexity. The method needs to do b-1 exponentiation operations, that is a is equal to a power e mod n. The first exponentiation algorithm that does this in 2 log base 2b operations. This method also uses GCD calculation, which needs log n cube operations. User can say that the complexity is somehow greater than order of b or order of 2 power nb exponential, where nb is the number of bits in b. Another problem is that the algorithm may fail. The probability of success is very small unless b is very close to square root of n. Pollard-Rowe method. In 1975, John M. Pollard developed a second method for factorization. The Pollard-Rowe factorization method is based on the following points. Assume that there are two integers, x1 and x2, such that p divides x1 minus x2 but n does not. It can be proven that p is equal to GCD of x1 minus x2, n. Because p divides x1 minus x2, it can be written as x1 minus x2 is equal to q into p. But because n does not divide x1 minus x2, it is obvious that does not divide n. This means that GCD of x1 minus x2, n is either 1 or a factor of n. The following algorithm repeatedly selects x1 and x2 until it finds an appropriate pair. Choose x1, a small random integer called the seed. Use a function to calculate x2 such that n does not divide x1 minus x2. A function that may be used here is x2 is equal to f of x1 is equal to x1 square plus a. A is normally chosen as 1. Calculate GCD of x1 minus x2, n. If it is not 1, the result is a factor of n. Stop. If it is 1, return to step 1 and repeat the process with x2. Now user is calculating x3. Note that in the next round the user starts with x3 and so on. If user lists the values of x using the Pollard-Rowe algorithm, the user sees that the values are eventually repeated, creating a shape similar to the Greek letter rho as shown in the following figure. To decrease the number of iterations, the algorithm has been slightly modified. The algorithm starts with a pair x0, x0 and iteratively computes x1, x2, x2, x4, x3, x6 and so on up to xi, x2i using xi plus 1 is equal to f of xi. In each iteration, user can use the function from step 2 once to calculate the first element in the pair and twice to calculate the second element in the pair. Complexity. This method requires square root p arithmetic operations. However, because user expects up to be smaller or equal to, the user expects to do n power 1 by 4 arithmetic operations. This means that the bit operation complexity is order of 2 power nb by 4 exponential. Fermat's and Euler's theorem. In this video, we are going to see about Fermat's and Euler's theorem. Fermat's and Euler's theorem plays important role in public key cryptography. Fermat's theorem. Fermat's theorem states the following. If p is prime integer and a is a positive integer not divisible by p, then a power p minus 1 is equal to 1 mod p. Proof. Consider a set of positive integer less than p is equal to set 1, 2 and so on up to p minus 1. Multiply each element by a modulo p to get x is equal to set a mod p, 2a mod p and so on up to p minus 1 a mod p. None of x elements is equal to 0 because p does not divide a. No two of the integers in x are equal. Solution. Assume j into a is equal to k into a mod p, where 1 is less than or equal to j less than k less than or equal to p minus 1. Because a is relatively prime to p. Eliminate a from both sides of equation. Ja is equal to ka mod p. J is equal to k mod p. This equality is impossible because positive integer j and k are both less than p. Hence, p p minus 1 elements of x are all positive integers with no two elements are equal. So x consists of integers set 1, 2 and so on up to p minus 1. Now a into 2a and so on up to p minus 1 is congruent to 1 into 2 and so on up to p minus 1 mod p. A power p minus 1 into p minus 1 factorial is congruent to p minus 1 mod p because p minus 1 factorial is relatively prime to p. AP minus 1 is equal to mod p, hence the proof. An alternative form of Fermat's theorem. If p is prime and a is a positive integer, then a power p is equal to a mod p. The first form of the theorem requires that a be relatively prime to p, but this form does not. P is equal to 5, a is equal to 3, a power p is equal to 3 power 5, which is equal to 243, which is congruent to 3 mod 5 equal to a mod p. P is equal to 5, a is equal to 10, a power p is equal to 10 power 5, which is equal to 10,000, which is congruent to 10 mod 5, which is congruent to 0 mod 5, which is equal to a mod p. Euler's theorem. Before presenting Euler's theorem, user need to introduce an important quantity in number theory referred to as Euler's totient function, pi of n. It is defined as the number of positive integers less than n and relatively prime to n. Determine phi of 37 and pi of 35. 37 is a prime. All of the positive integers from 1 through 36 are relatively prime to 37. Thus, phi of 37 is equal to 36. To determine phi of 35, user need to list all positive integers less than 35 that are relatively prime to it. 1, 2, 3, 4, 6, 8, 9, 11, 12, 13, 16, 17, 18, 19, 22, 23, 24, 26, 27, 29, 31, 32, 33, 34. There are 24 numbers on the list, so pi of 35 is equal to 24. The value pi of 1 is without meaning but is defined to have the value 1. It should be clear that for a prime number p, pi of p is equal to p minus 1. If suppose p and q, p is not equal to q are two prime numbers, then n is equal to pq. Pi of n is equal to pi of p into q is equal to pi of p into phi of q, which is equal to p minus 1 into q minus 1. Proof. To see that pi of n is equal to pi of p into pi of q, consider a set of positive integers less than n. The set 1 and so on up to pq minus 1. Integers in this set that are not relatively prime to n. The set p, 2p and so on up to p minus 1 into q and q, 2q and so on up to p minus 1 into q. Accordingly, pi of n is equal to pq minus 1 minus q minus 1 plus p minus 1 is equal to pq minus p plus q plus 1 is equal to p minus 1 into q minus 1, which is equal to pi of p into pi of q. Some values of Euler's totient function n, pi of n. N is equal to 1, pi of n is equal to 1. N is equal to 2, pi of n is equal to 1. N is equal to 3, pi of n is equal to 2. N is equal to 4, pi of n is equal to 2. N is equal to 5, pi of n is equal to 4. N is equal to 6, pi of n is equal to 2. N is equal to 7, pi of n is equal to 6. N is equal to 8, pi of n is equal to 4. N is equal to 9, pi of n is equal to 6. N is equal to 10, phi of n is equal to 4. Example: phi of 21 is equal to phi of 3 into phi of 7 is equal to 3 minus 1 into 7 minus 1, which is equal to 2 into 6 is equal to 12, where the 12 integers are set 1, 2, 4, 5, 8, 10, 11, 13, 16, 17, 19, 20. Euler's theorem states for every a and n that are relatively prime, a power phi of n is congruent to 1 mod n. Proof: consider set of integers r is equal to set x1, x2 and so on up to x phi of n. That is, each element x of R is a unique positive integer less than n with GCD of xi, n is equal to 1. Now multiply each element by a modulo n. S equal to set ax1 mod n, ax2 mod n and so on up to ax phi of n mod n. The set S is a permutation of R by a is relatively prime to n, ax1 also relatively prime to n. So all member of S is less than 0 or relatively prime to n. If no duplicates in S, if axi mod n is equal to axj mod n, then xi is equal to xj. Therefore, product over I is equal to 1 to phi of n, axi mod n is equal to product over I is equal to 1 to phi of n xi. Product over I is equal to 1 to phi of n axi is equal to product over I is equal to 1 to phi of n xi mod n. A power phi of n into product over I is equal to 1 to phi of n into xi is equal to product over I is equal to 1 to phi of n xi mod n. A power phi of n is equal to 1 mod n. Here completes the proof. This is the same line of reasoning applied to the proof of Fermat's theorem. Example: a is equal to 3, n is equal to 10. Phi of 10 is equal to 4 into a power phi of n is equal to 3 power 4 is equal to 81, which is equal to 1 mod 10 is equal to 1 mod n. A is equal to 2, n is equal to 11. Phi of 11 is equal to 10 into a power phi of n is equal to 2 power 10, which is equal to 1024 is equal to 1 mod 11 is equal to 1 mod n. The alternate form of Fermat's theorem: a power phi of n plus 1 is equal to a mod n. Testing for primality. In this video, we are going to see about testing for primality. In many cryptographic algorithms, it is necessary to select one or more large prime number at random. Making use of the deterministic algorithm enables for finding primes. Miller-Robin algorithm. Miller-Robin algorithm is proposed by Miller and Robin, proposed to rest a large number of primality. Let any positive odd integer n is greater than or equal to 3 can be expressed as n minus 1 is equal to 2 power k into q, with k is greater than O, q odd. N minus 1 is an even integer. Divide n minus 1 by 2 until the result is an odd number q, for a total of k divisions. If n is expressed as a binary number, then the result is achieved by shifting the number to the right until the rightmost digit is 1 for a total of k shifts. The two properties of prime numbers are: Property 1. If p is a prime, a is a positive integer, a is less than p. Then a square mod p is equal to, if either a mod p is equal to 1 or a mod p is equal to minus 1 mod p is equal to p minus 1. By the rules of modular arithmetic, a mod p is equal to a square mod p. Thus, a mod p is equal to 1 or a mod p is equal to minus 1. Then a square mod p conversely. If a square mod p is equal to 1, then a mod p the whole square is equal to 1, which is true only for a mod p is equal to 1 or a mod p is equal to minus 1. Property 2. Let p be a prime, p is greater than 2. P minus 1 is equal to 2 power k into q, with k is greater than 0, q odd. A integer, 1 less than a less than p minus 1. Then one of the two following conditions is true. A power 0 is congruent to 1 modulo p, that is a power q mod p is equal to 1, or equivalently a power q is congruent to 1 mod p. Fermat's theorem. Its sketch. A power n minus 1 is congruent to 1 mod n if n is prime. P minus 1 is equal to 2 power k into q. User know that a power p minus 1 mod p is equal to a square. Hence the sequence of numbers. A q mod p, a2 q mod p, a4 q mod p, and so on up to a power 2 power k minus 1 into q mod p, a power 2 power k minus 1 into q mod p. Last number in the list value is 1. Each number in the list is the square of the previous number, therefore any one of the possibilities coming is true. The first number on the list and therefore all subsequent numbers on the list equals 1. Some number on the list does not equal 1, but its square mod p does equals 1. By virtue of the first property of prime numbers defined above, user know that the only number that satisfies this condition is p minus 1. This completes the proof. The procedure test takes a candidate integer n as input and returns the result composite if n is definitely not a prime and the result inconclusive if n may or not be prime. User know that a power p minus 1 mod p is equal to a square. Test of n. Find integer k, q with k is greater than 0, q odd, so that n minus 1 is equal to 2 power k into q. Select a random integer a, 1 is less than a less than n minus 1. If a power q mod n is equal to 1, then return inconclusive. For j is equal to 0 to k minus 1, do if a power 2 by q mod n is congruent to n minus 1, then return inconclusive. Return composite. A deterministic primality algorithm. This is also called as AKS Agarwal-Kayal-Saxena algorithm, but does not appear to be efficient as Miller-Robbins algorithm. Distribution of primes. The prime number theorem states that the primes near n are spaced on the average 1 every ln n integers. Thus, on average 1 would have to test on the order of ln of n integer before a prime is found. Because all even integers can be immediately rejected, the correct figure is 0.5 ln of n. For example, if a prime on the order of magnitude of 2 power 200, then about 0.5 ln 2 power 200 is equal to 69 trails would be needed to find a prime. The Chinese remainder theorem CRT. In this video, we are going to see about the Chinese remainder theorem CRT. The Chinese remainder theorem is one of the oldest theorems in the number theory. It results congruencies in number theory and its generalizations in abstract algebra by Chinese mathematician Sun Tzu. M is equal to product over I is equal to L to K Mi, where Mi are pairwise relatively prime. Any integer a in Zm by a k tuple whose elements all in Zm using the following correspondence. A is equivalent to A1, A2 and so on up to AK. A belongs to Zm. AI belongs to Zm. AI is equal to A mod Mi for 1 is less than or equal to I less than or equal to K. The CRT makes two assertions. Mapping of equation A equivalent to A1, A2 and so on up to AK is one-to-one correspondence called as bijection. CRT is concerning arithmetic operations follows from the rules of modular arithmetic. A is equivalent to A1, A2 and so on up to AK. B is equivalent to B1, B2 and so on up to BK. Manipulates number mod m in terms of tuples of small numbers. Algorithm. Chinese reminder. Input. Integer tuple m1, m2 and so on up to mr pairwise relatively prime. Integer tuple c1 of mod m1, c2 of mod m2 and so on up to cr of mod mr. Output. Integer x is less than m is equal to m1, m2 and so on up to mr. M equivalent to m1, m2 and so on up to mr. For I from 1 to r, do yi equivalent to m by mi inverse mod mi. Lmi equivalent to yim by mi. Return. Summation of I is equal to 0 to r. Lmi ci mod m. If GCD of mi, nj is equal to 1, for 1 is less than or equal to I, or less than or equal to j, or less than or equal to r, then for m is equal to m1, m2, and so on up to mr. Zm is isomorphic to Zm1 into Zm2, and so on up to Zmr, and the isomorphism f Zm tends to Zm1 into Zm2 and so on up to Zmr is f of x is equal to x mod m1, x mod m2 up to x mod mr. This isomorphism is very useful in the study of cryptographic systems or protocols which use groups module composite integers. Applications. In the RSA algorithm, calculations are made modulo n, where n is a product of two large prime numbers p and q, 1024, 2048 or 4096-bit integer. N are commonly used making calculations in very time-consuming. By the Chinese remainder theorem, however, these can be done using isomorphic ring, takes much faster. RSA algorithm implementations using this isomorphism are more susceptible to fault injection attacks. Secret key sharing using the Chinese remainder theorem. Discrete logarithms. In this video, we are going to see about discrete logarithms. Discrete logarithms are fundamental to a number of public key algorithms such as Elgamal encryption, Diffie-Hellman key exchange, and the digital signature algorithm. Newer cryptography applications use discrete logarithms in cyclic subgroups of elliptical curve cryptography. The power of an integer module n. Let us consider Euler's theorem. A power pi of n is congruent to 1 mod n, where a and n are primes. Pi of n gives number of positive integers less than n and relatively prime to n. Let's phi of n is equal to m, then a power m is equal to 1 mod n. The least positive exponent m is referred as the order of a mod n, the exponent to which a belongs mod n. the length of a period generated by A. Let us see an example. Powers of 7 modulo 19 expressed in above equation as A power m is congruent to 1 mod n, which implies 7 power m is congruent to 1 mod 19. Therefore, 7 and 19 are relatively prime. Let us take the powers like 1, 2, 3, 4, 5 and so on. 7 power m is congruent to 1 mod 19, which implies 7 power 1 is congruent to 7 mod 19. 7 power 2 is equal to 49 is equal to 2 into 19 plus 11, which is congruent to 11 mod 19. 7 power 3, which is equal to 343, equal to 18 into 19 plus 1, which is congruent to 1 mod 19. 7 power 4 is equal to 2401 is equal to 126 into 19 plus 7, which is congruent to 7 mod 19. 7 power 5 is equal to 16,807 is equal to 884 into 19 plus 11, which is congruent to 11 mod 19. It is repeating, hence the length of the period is the smallest positive exponent m, such that 7m is congruent to 1 mod 19. Let's take the powers of A modulo 19, where for all positive A is less than 19. From the above table, all sequence ends in 1. The length of a sequence divides phi of 19 is equal to 18. The sequence of length 18 which generates set of non-zero integers modulo 19, such integers are called primitive root of the modulo 9. Highest possible I exponent to which a number can belong, mod n, is phi of n. It is referred as primitive root of n. If A is primitive root of n, then its powers A square and so on up to A power phi of n. If A is primitive root of P, prime number, then its powers A square and so on up to A power P minus 1. Primitive roots for 19 are 2, 3, 10, 13, 14, 15. Logarithms for modular arithmetic. An analogous function exists for modular arithmetic. The logarithm of a number is defined to be the power to which some positive base except 1 must be raised in order to equal the number, that is, for base x and for a value y. Y is equal to x power log x of y. The properties of ordinary logarithms include log base x of 1 is equal to 0, log base x of x is equal to 1, log base x of y z is equal to log base x of y plus log base x of z. Log base x of y power r is equal to r into log base x of y. Primitive root A for some prime number p from 1 through p minus 1. By modular arithmetic, b is congruent to r mod p for some r, where 0 is less than or equal to r, less than or equal to p minus 1. Primitive root A of prime number, user get unique exponent I, such that b is congruent to a power I mod p for some r, where 0 is less than or equal to I, less than or equal to p minus 1. I, that is exponent, is referred as discrete logarithm of number b for base a mod p. It can be expressed as d log base a comma p of b is equal to 0 because a power 0 mod p is equal to 1 mod p, which is equal to 1. d log to the base a comma p of a is equal to 1 because a power 1 mod p is equal to a. Now consider from above equation b congruent to ai of mod p. X is equal to a power d log base a comma p of x mod p. Y is equal to a power d log to the base a comma p of y mod p. Now rules of modular multiplication. Let xy is equal to a power d log to the base a comma p of x mod p. Xy mod p is equal to x mod p y mod p into mod p. A power d log to the base a comma p of xy mod p is equal to a power d log a comma p of x mod p. A power d log a comma p of y mod p into mod p is equal to a power d log to the base a comma p of x plus d log to the base a comma p of y into mod p. Now recall Euler's theorem where a and n are relatively prime. A power phi of n is congruent to 1 mod a. Any positive integer z can be expressed as z is equal to q plus k into phi of n with 0 less than or equal to q less than qca. By Euler's theorems, a power z is congruent to a power 0 mod n if z is congruent to q mod phi of n. Applying this to foregoing equality, that user having d log to the base a comma p of xy, which is congruent to d log to the base a comma p of x plus d log to the base a comma p of y mod phi of p, generating d log to the base a comma p of y per r is congruent to r into d log to the base a comma p of y into mod phi of p. Logarithms. Above equation shows the analogy between true logarithms and discrete logarithms. Calculation of discrete logarithms. Consider equation y is equal to g per x mod p. Knowing value of g, x, p, compute y. In general, computing x is very difficult. For computation, fastest known algorithm for taking discrete logarithms modulo a prime number is of the order e power ln p to the power 1 by 3 into ln of ln p to the power 2 by 3 can be used, but it is not feasible for large primes.